Hi, I'm Hongbo Kang from Tsinghua University. I'm very happy today to introduce our work, PIM-tree, a skew-resistant index for processing memory. This is a joint work with following collaborators. We are a group designing algorithms and computer systems, and special thanks goes to ABUMPIMP for their great product and the help they offered during the development of this work. Briefly go through the memory wall problem as we all know this. Memory wall problem shows on two aspects. The first one is on the speed, including both bandwidth and latency, and the other side is the power consumption. And nowadays, data movement is becoming the key bottleneck of many applications, especially those data-intensive applications, which is quite important in today's work. And about processing memory is a quite old idea, but it's a more popular reason in recent years because of the memory wall problem. And we believe that the key idea of processing memory is cores or compute power in the memory module to avoid the data movement between the memory or data storage and the compute site. So with the emerging PIM architecture, one natural question to ask is how to design efficient systems upon this. And our approach is to build a theoretical model that captures the key ideas of PIM systems and design theoretically efficient systems as a guidance. One of our previous work in 2021 gives out such a model. We call it the processing memory model. We model the systems with three components. A multi-core CPU side with a LLC shared cache of M words, PIM modules, each with one core that can only visit its local memory and a local memory, and a network. We assume the problem size is n words in total, so each local memory is n over p sized. The PIM module assumes a BSP-style execution, which contains multiple synchronous rounds separately for CPU computation, PIM computation, and communication. Three cost metrics are used. We use CPU work and span to measure CPU computation. PIM time and I/O time respectively measures the PIM computation and communication. Note that each synchronous round must wait for the slowest PIM module to finish the round, hence we need the term maximum in the cost metrics. With the model constructed, we can design PIM-friendly indexes. We choose pointer chasing indexes as our topic because it is a core block for in-memory storage and is widely known as a victim to its serial random memory access pattern. In our design, the index stores key value pair data and support 5 types of operations: get, insert, delete, predecessor or successor, and range query. We assume a batch parallel execution where operations are grouped into same type batches for parallel execution. In this work, we focus on skip lists to get an easier implementation for parallel inserts and deletes. We believe most techniques are applicable to other ordered indexes like B-tree and leave them as interesting future work. There are previous works trying to design PIM-friendly indexes. They utilize a similar structure. We call it range partitioning skip lists, where key space is partitioned into disjoint ranges, and each PIM module stores a continuous fraction of the data by a local skip list. In this way, they achieve low communication. The communication is asymptotically constant for point operations. Meanwhile, they exploit the parallelism while queried keys fall into different ranges. However, this design is vulnerable to skewed operations, which is a common case in practice. In case of an uneven distribution of keys, there can be severe load balance issue among PIM modules. Throughout this talk, all examples assume a 4 PIM module system, each PIM represented by a unique color. In the hardware we use, the hardware by ABUMPIMP, the platform has over 2,000 PIM modules. Here, we want to find the predecessor for keys 7, 8, 9, and 10. In this example, the whole batch is sent to PIM module 3 for a local search, while all other PIMs are literally idle. This completely serialized the process, causing severe performance downgrade. There's another straightforward design which avoids such imbalance: random mapping. We start from a standard skip list and send each node to a random PIM module. The random distribution helps avoid imbalance. Every time you move between nodes of different color, a communication round is required for this remote pointer. For example, to get result 15, You communicate with the green PIM module first, and then the purple one, then yellow one, until reaching the result. As you can see, the drawback of this solution is its poor data locality. While most pointers are remote, a single search requires all log n rounds. In fact, there's no asymptotic communication reduction compared with traditional non-PIM architecture. From the previous two examples, we seem to find an inner contradiction between load balance and communication reduction. We should also take space consumption and update costs into consideration. Otherwise, we could simply replicate the index on all PIMs for optimal load balance and communication. As a result, this gives us a principal problem to consider when we design PIM-based indexes as well as all PIM systems. Can we find a sweet spot between space and update cost, load balance, and communication? The answer is going to be yes. Our PIM design achieves provable and practical efficiency in throughput, communication, space, and update cost. With our design principles, we present here the major contributions we made in designing the PIM-tree. We start by random mapping structure and apply 4 optimizations on that. We replicate the upper part to reduce communication. We apply a push-pull search technique for lightweight load balance. And we use shadow subtree and chunking to further provide locality. Our improvements are inspired by observations in the tree structure. Take this B tree for instance. The upper part is frequently accessed in searches, but its size is relatively small, and it is rarely updated. This brings our first optimization. We can replicate the upper part in all PIM modules. Recall that each PIM has asymptotically n over p space, so it can store an upper part with such size. The upper part is log n over p levels tall, and the lower log p levels remain distributed. This replication takes linear space. When executing search queries, since all upper parts are exactly same copies, the queries can be evenly distributed to PIMs, and searching through the upper part only access local PIM memory. By avoiding communication in the upper part, we reduce search communication from log n to log p. For update cost, the amortized cost of maintaining coherent upper part is constant because very few updates go all the way up to the upper part, canceling out the overhead factor of replication. Before stepping forward to further communication reduction, one challenge remains in load balance, node-wise contention. In this example, we find the predecessor for key 1, 8, 9, and 10. Operations are evenly sent to PIMs for the upper part, and results are sent back to CPU, nicely balanced. Imbalance show up in the lower part. Queries can concentrate on this single node 7, causing work concentration on the green PIM module, hence loading balance. Even with random mapping, operations can concentrate on few nodes, and the node-wise contention can destroy load balance. Our solution to this is a push-pull search. The idea is simple. For nodes with few queries, send queries. For nodes with too many queries, fetch the node and do computation on the CPU side. An interesting observation is that while pushing queries is a basic technique for distributed computing, fetching data is what all machines do in today's shared memory architecture. A simple combination of the most fundamental solutions of the two different architectures directly gives a lightweight solution for load balance. Next, a shadow subtree. The shadow subtree is a partial replication strategy, providing vertical locality in the lower part. We further divide the lower part horizontally into L2 and L1. Due to the space and update cost, shadow subtree is only applied in L2. L2 nodes cache their descendant search tree. This cache structure is called shadow subtree. Take this yellow node on the top left as example. This is its descendant search tree. This descendant tree only includes L2 nodes. Besides, the right part isn't included because we won't walk to it from the yellow node. We use this red downward pointer instead. We cache this tree inside the node, including all internal pointers and outward pointers. Similar structure is applied for all L2 nodes. With shadow subtree, if there's no contention on an L2 node, the whole L2 search process can be done within one PIM module locally. Please refer to the paper about how push-pull search cooperates with shadow subtrees for load balance. After shadow subtree, the PIM-tree has a 3-layer structure. By applying different replication strategy to different layers with different amount of data, we enable efficient queries and updates with load balance. The height of each layer is carefully decided according to the number of PIM modules. We set the height of L1 to log p, so search communication is O log p, because L3 and L2 take constant words communication after replication. Meanwhile, we achieve linear space consumption and constant words communication for updates after search. The key idea is in the red box. The replication is only applied to a small proportion of infrequently updated data, so the overhead is canceled out. The last optimization, chunking, aims at reducing communication caused by horizontal remote pointers. We merge horizontal nodes together into chunks, so all communication over horizontal searches can be saved. Chunking helps improve all previous bounds from log2 base to log b base, where b is the average chunk size. In practice, it's 16. PIM-tree achieves good results in the PIM model. It achieves guaranteed load balance against adversary-controlled skew. The communication is reduced to O log b log bp per operation for search and update. In practice, it only takes 3 or 4 communication rounds regardless of skew. The space consumption is linear. We carry out our designs on real machine, the machine in the UPMEM platform, which has PIM-equipped DIMMs as drop-in replacements to traditional DRAM DIMMs. Although we didn't know their products when we first proposed the PIM model, they match well. The machine has multi-core CPUs as a CPU side, over 2,000 PIM modules as a PIM side, and the memory bus as a connecting network. Due to the time limit, I cannot show all our experiment results. Here are a few figures chosen from our experiments. The first one carries out experiments over PIM-based range partitioning indexes. The range partitioning scheme is faster on non-skewed case, but we are up to 59 times faster for skewed cases. The second one carries out experiments over some state-of-the-art shared memory indexes. We achieve comparable throughput and win strictly in memory accesses in all cases. And since the publication of this paper, we've identified overheads in the software and designed a lightweight framework for faster communication. Here are some early stage results. So this is a lightweight program designed on the UPMEM SDK that's aimed at optimizing communication for small batches. And these are the results for scatter and gathers for buffers over of 1 to 1,000 kilobytes with all DPUs on a machine with 32 ranks and 2,000 PIM modules. And we can see for small buffers, the bandwidth gathered by this new Lightwork API can be a lot higher. And we apply this new interface to PIM-tree and validate the result on the Wikipedia dataset. And on the machine that has 32 ranks and 2,000 PIM modules functioning, we achieve a speed up of over 30% for predecessor queries. The speed up is not so much for the insert queries because the insert part is much more CPU bound. And the SDK is named UPMEM SDK Lite. It's on GitHub. As a summary, these are the key takeaways. PIM is emerging as a solution to reduce data movement. Prior works are vulnerable to skew, but PIM-tree is skew-resistant with provable and practical efficiency. To achieve this, we designed a 3-layer structure with different replication strategy, a lightweight load balance solution, push-pull search, and chunking. And all codes can be found by this URL. And thanks for listening.